Good morning, everyone, and welcome to the first workshop where we inaugurate our Hydrogen Technology Observatory. Last April 9th, during our first Hydrogen Technical Day, our CEO, Arturo Gonzalo, announced our Hydrogen Technology Observatory. This observatory is a meeting point and a platform to showcase all the technological advancements around the development of the renewable hydrogen value chain. Renewable hydrogen is the technological solution to decarbonize the gas-intensive Spanish industry, and it is Europe's major commitment for replacing fossil fuels in large-scale industry and heavy transport in the medium and long term. However, the production of this renewable hydrogen relies on intermittent and less manageable resources such as wind or solar power, making underground hydrogen storage a key component in the development of this new energy vector. That's why today we have Emmanuel Kermarrec, Storengy Head of Geosciences and Solutions Mining, and Rosa Nieto, Enagás Engineering and Project Director, to talk about the state-of-the-art underground hydrogen storage options available and their development in the coming years. Following them, we have Guillermo Garcia, H2SITE Commercial Manager, and Igor Pagazaurtundua, Enagás Head of Innovation and Technological Development, who will also discuss a hydrogen purification project closely related to underground storage. Thank you for joining us and sharing your time and experience with us. Finally, I would like to invite all of you who are listening to join this Hydrogen Technology Observatory that we offer you open. Our coordinator, Igor Pagazaurtundua, is available for contact. Thank you very much. And Rosa and Emmanuel, can you start?
So, good morning, everybody, and thank you, Susana, for your introduction. To talk about the state-of-the-art of hydrogen storages, both in salt caverns and porous media, we are delighted to speak to Mr. Emmanuel Kermarrec from Storengy. Welcome, Emmanuel. Emmanuel is a mechanical engineer with more than 20 years of experience in the gas industry. He has held several positions as operational manager in France, UK, China, etc. And today, as the head of Geosciences and Solution Mining for Storengy, he's working to enhance and adapt underground energy storages. And his company, Storengy, is the storage operator leader in Europe in underground gas storages, and the fourth worldwide, with 70 years of experience and 21 storage sites in France, Germany, and UK, both in salt cavities and porous media. So, starting with salt cavities, for those not familiar with the technologies, salt caverns are lit in deep and thick salt layers by injecting water to create hollow spaces where gas can be stored at high pressure. These caverns have several advantages for the storage of hydrogen, such as high tightness, absence of chemical reactivity, possibility of creating custom-made caverns, and capacity to handle high injection and withdrawal rates. Emmanuel, Storengy has extensive experience in the storage of natural gas in salt caverns and is currently involved in several projects to study the technical and economic feasibility of storing hydrogen in this type of infrastructure. So my first question is, what challenges does the storage of hydrogen in salt caverns pose, especially in terms of high frequency and fast cycling cycles between injection and withdrawal? And what are the differences with natural gas due to the thermodynamic behavior of hydrogen?
Thank you, Rosa. So first of all, Storengy, what we think is we can store pure H2 in salt cavern. Think about that because there are already 4 storages around the world storing for dedicated purpose and for strategical purpose pure H2 in salt cavern. 3 in the US, 1 in the UK. So we can store pure H2 in salt caverns. There is no question about that. But the challenges for us today is to demonstrate that underground hydrogen storage in any kind of media are safe and they will bring benefit to the future energy system. Now, what does it mean? We know all, hopefully you know all, or I will recall you, that underground gas storage today, or gas storage today, are 3 values, 3 key values. The first one, well known due to the crisis, Ukrainian war, this is the security of supply. This is the first added value. The second value is the system value. It means you can optimize, especially your pipeline, rather than to increase the size in order to manage the peak. So you reduce the capex on some gas infrastructure. The third value of the storage is what we call arbitration value. To put in a nutshell, to be able to trade, make some trading, and to smooth the price of the gas you may deliver to your customer, for example. But when we talk about underground hydrogen storages, there are 2 more added values. This is the one, they are maybe a little tricky, but I'm going to focus a little bit on them because it will make the link with what you talk about cycling. The first one, the first added value regarding to UHS is what we call the environmental value. What does it mean? It means that at some point in the future, we shall be able to produce electricity using renewable and green gas instead of fossil fuel. And that thanks to underground hydrogen storages. It won't be possible without underground hydrogen storages. And the last one, the key value, it's a tricky one again, what we call the kickstart value. What is the kickstart value? The kickstart value for underground hydrogen storages will allow the development of renewable energy. It's what you started to mention in the introductions. In fact, underground hydrogen storages will allow the development of the production of green gas based on renewable energy because underground hydrogen storages will balance the intermittency and the curtailment lead with what we call renewable. This is the 5th value of underground hydrogen storage. Okay, when you look at the last 3, arbitration value, trading, environmental value, and kickstart value. What do they need in order to bring benefit to the future energy system? They need to be able to withstand the curtailment. So it means they need to be able to bring flexibility to the system. This is where today we need to demonstrate that underground hydrogen storages will be able to do cycles. We talk about fast cycling. The more we are talking about, the more we are studying it, I don't think we will do cycling. We will do high frequency trading, which is a little different. Today we are thinking we are not filling and empty the cavity in one go, several times a year, but we will do very small variation intradays in order to withstand wind or solar and so on. And so today what we are looking for to demonstrate we can do we can do cycling and to manage high frequency trading. What does it mean in terms of safety? In terms of safety, it means we need to demonstrate all the equipment are able to withstand the variation of pressure. And we know about H2, compared to, for example, natural gas, there is this embrittlement effect, So it means we need to be able to ensure that with this variation, fast cycling variation of pressure inside the equipment, especially the wells, the subsurface, the above ground equipment, the right material will be chosen in order to withstand this variation and to keep safe the plant. Regarding the cavern, maybe you know about what we call MIT test, mechanical integrity test. It will be a major topic as well. Find what shall be a mechanical integrity test for a salt cavern that will do fast cycling. And the last, it's H2 itself. You know, the way H2 reacts when you got energy, the way you will manage H2 when you talk about attack zone, explosion area, we need to think about the H2 safety standards as well. What kind of process safety will be implemented of the next generation of plants that will be underground hydrogen storages. So then I will focus on the thermodynamical effect. When I started as a young engineer on the field, playing with natural gas, the technician told me, okay, you should know, guys, when you play with natural gas, when you decrease the pressure of natural gas by 1 bar, you will lose 0.5 degrees. This is the basic, what you need to know when you are a technician on the field. So this is the Joule-Thomson effect for natural gas. And so now when we talk about hydrogen, this is one of the fourth gas in the world not having the same behavior. The Joule-Thomson effect is reverted. When you will reduce the pressure, it shall increase the temperature. This is the case in adiabatic cases. So when you, if you take the pressure we'll play with around 80 bars, let's say. In fact, when you bleed 1 bar of H2 in an adiabatic enclosure, it will raise the temperature of 0.05 degrees. So it means it's 10 times less variation than CH4. So today what we think is, because we are going to do maybe high frequency training, it means we will withdraw and inject hydrogen only on a portion of the cavern. And based on the case that caverns are not an adiabatic system, in fact, having this effect, the thermodynamical effect will less affect the cavern than the one for CH4. So in fact, for us, the Joule-Thomson effect for H2 shall be a problem for the cavern. And we are able to modelize that today because we have the in-house tools to do that.
Okay, thank you. So you mentioned about the effect of the cycling on materials. Now, in the industry, there are also some discussions about whether tubing must be welded or threaded. What's Storengy's position on that?
Alors, it's a very interesting question. In fact, Storengy, at some point, we decided to weld our tubings in our cavities, in our new caverns for natural gas. And we decided to move back. So today, the position of Storengy is not to go for weld tubing, but to stay on threaded tubings. The reason is, if today we are able to manage welding on tubings, there are again some questions regarding the capability to weld tubings and accessories. In fact, we detect some failures between accessories, for example, subsurface landing nipples and tubings. Today, Storengy, the standard is threaded premium connections with threaded connection, not welding.
That's the same position as we agree.
But we experience welding tubing, and we had to do what we call dry work cover on salt cavern, which is a tough operation, you know, to remove all the tubes.
Okay. So what projects at the European level and of Storengy in particular are being undertaken to analyze the behavior of salt caverns with this mode of operation you mentioned of fast switching from injection to withdrawal?
We have 3 projects in France at the moment, and these projects, they will be replicated to UK and Germany. We have a first project near Manosque with geomethane, and so we did not inject 100% of H2, but we injected maybe 300 or 400 kilos of H2 in order to demonstrate that H2 will not, we won't get any stratifications inside the cavern. So in fact, the H2 will mix with the remaining CH4. Okay, but regarding pure H2, we have one project near Lyon called Hipster Project. We got some delayed at the moment on that project, but the goal of this project is to be able to not to demonstrate the cavern itself will withstand hydrogen, is to demonstrate that we are able to do several cyclings on the cavern without leaks, especially on the wells. And so we are going to inject 3 tons of hydrogen in the following days. And then we are going to do 100 cycles, so full cycles, not teeny variations, in order to see the behavior of the equipment we installed on the cavern. And the last one is the French Hydrogen Germany project near Manosque, where Enagás is member of the advisory board, I think. This project, it will be more in 2028, but we're just starting on the project. In that case, it will be to trade a cavern filled with at least 1,000 tons of hydrogen. In that case, we will really withdraw and inject hydrogen into the cavern. In the Hipster project, we have no output. In fact, it's a kind of virtual trading in the Hipster project. You play with the brine in order to increase and decrease the pressure. But in the French project, we will really withdraw and inject gas from the cavern. And in order to do that, in fact, we have 2 caverns. One will act as a buffer to the other one. So it will be 1,000 tons of hydrogen. Again, all these projects today are very limited in terms of test, because the more we are working on projects, the more we may need a pipeline, hydrogen infrastructures. When we talk about 1,000 tons of hydrogen to be injected, it cannot be done using trucks. That's very difficult, especially when you want to do the test. And today, the limitation is linked with the transmission pipeline. There is no transmission pipeline, no infrastructure around in order to do all the tests we would like to.
Thank you. And my last question regarding salt cavities, and it's a question that connects also with the next panel. There are many discussions about the required purity of hydrogen in the network. This is a parameter that can greatly affect the purification facilities of hydrogen extracted from the cavities. What degree of purity can be expected once the hydrogen is withdrawn? How can we determine the impurities that will accompany hydrogen to design the treatment facilities?
It's a key question, because we don't know. As it is the goal of the Hipster project, to be able to determine what kind of hydrogen we will withdraw from the cavern. And there are 2 parameters, in fact. There is the quality and the flow rate. Because tomorrow we are talking about high flow rate of hydrogen to be withdrawn. It's another parameter. When it's low flow rate, it's easier to do purification, but when we are talking about ton per hour of several tons per hour of hydrogen to be withdrawn, it's another topic. So today, what we think, what Storengy think, we think that the salt cavern and brine may not react with pure hydrogen. So we don't we are not thinking about any of a new cavern to add any new compartment. Won't be the case for conversion. So today, what we think is, okay, we'll get moisture and water from the cavern. So we'll set the hydration plant. On the IFTER project, even if we are not sure about that, because there is no paper demonstrating anything already, we don't think we'll get H2S from the cavern, but we installed the desulfuration unit in case. We are not sure. But today we don't see how we could get H2S from the cavern. And regarding the quality of the hydrogen, the first question is, what will be the quality of hydrogen will we get from the network? There is no standard at the moment about the quality of hydrogen we get from the network. I read some project telling that the quality of the French network will be 98%. I heard about lobbying in Europe about 98% of hydrogen as well in Europe. But I know that in Germany, some companies are pushing for 99.5% of H2 quality on the network. In that case, we think that we will need some solution of purification. We don't know to purify what, but we're pretty sure we'll need some solution of purification in that case. The difficulty is it may increase the cost of the storage, and this is not what we want at the moment. We want to try to provide a low cost of hydrogen on the market. Because the technology that will be required in order to purify, we need to withstand very high flow of hydrogen and a high amount of hydrogen. When I talk about very high flow, it should be something like 4, 5, 6 tons per hour of hydrogen to purify. So let's see. We'll see. We'll see.
We'll see. Okay, so moving on to hydrogen in storage in porous media. Porous media are geological formations that contain interconnected pores between the rock grains, where the gas is stored, or the gas also can be stored in fractures. The porous media can be depleted gas fields or deep saline aquifers. There are many underground gas storage in porous media in Europe. However, their feasibility must be studied one by one site due to bacterial reactivity, chemical reactivity, fingering, tightness issues. In our particular case, Enagás has obtained very encouraging lab results in Gela storage with samples from water reservoir and from cores that show quite little bacterial reactivity, but further studies need to be done. Briefly, Emmanuel, could you tell us what projects of Storengy in porous media are underway or planned, and what are your expectations regarding the possible repurposing of some storages?
It's another very interesting question. Today, in the last paper I read, it was in April or March, in 2050, the amount of storage that we may need in Europe shall be around 270 terawatt-hour of storage. 270. It's, let's say, it's 1,000 of cavern to be developed by 2050. Today, in the pipes, not only maybe the pipes, early study, we have maybe only 20 terawatt-hour of project in Europe. Taking the fact that in order to develop new assets or to convert assets takes time, and that need to have the right geological conditions, at some point you need to consider porous media. There is a but. There is a but because Storengy will also think that fossil fuel will not disappear. Natural gas, methane will not disappear by 2050. We also think that maybe the usage of methane will drop by 50% by this time, 2050. But we'll still need storage for methane. And today, the challenge we got at Storengy for the porous media is to ensure that our storages are able to store biomethane, e-methane, all that kind of stuff. Because biomethane, per generation of biomethane, may, except if they got purification unit at the producing side, may get O2, oxygen. And so oxygen may have an effect on the porous reservoir. Biomethane of second generations will get hydrogen, except if they put purification unit at the outlet of their biomethane plant, which is not the case today. So we may have some percentage of H2 inside the mix of the methane. So the challenge today is to demonstrate that the existing porous media is able to withstand maybe 5%, 6%, I don't know, of hydrogen, not 100%. And this is what we are doing. We are taking each media storage and we're taking cores, water, we try to get the bacteria and so on, we put it in a lab and we see what's happened. And to be honest, sometimes we are wondering what's happened. What we know in some porous media, it's possible to inject hydrogen. Because in 1956, the 50s, in fact, when we developed our first gas storage in France, near Paris, it was not natural gas, it was town gas. Gas made of coal and water. And the gas made of coal and water composition was 40% of hydrogen. So we know it's possible to store town gas and with a gas with high percent of hydrogen, which is good news for the storage. There is a but. When we get the archives, the but is when we withdraw the gas, the composition is not the same anymore. We have more methane than hydrogen injected. In that storage, we demonstrated that by injecting H2, the H2 and the bacteria and so on will get all the CO2, and we call a reaction called methanation in situ. That's storage. So for this storage, if you fill it with pure hydrogen, I'm not sure we'll get the hydrogen back. On other storages, especially the one when you got a little of H2SITE, so sulfur inside of your storage, as per the lab experiment we did, to put 1% of hydrogen in that storage will create a massive amount of H2S. So today it's a challenge for us only to get some percent of hydrogen. But as you said, this reaction depends on the rocks, the storage, the water, the history, the bacteria inside. And so in some cases, you'll be lucky and you will find a depleted reservoir or reservoir that will not react with hydrogen. In that case, you are lucky. But it's more, you need to look at each site by site, what may happen. And then the difficulty is, okay, you have a lab effect, but what is the scale-up effect? What's happened in reality? So after the lab test, I encourage you to do pilot test to see what's happened in reality.
Okay. Thank you. And to wrap this briefing session, we can say that the storage on salt cavities is technically viable and a competitive option. In porous media, it has to be studied side by side because it depends on many different parameters. Storengy and Enagás are involved in several innovative projects to adapt their assets to hydrogen and to contribute to the energy transition. However, the storage of hydrogen also poses some challenges that require more research and more development, such as the optimization of injection and withdrawal cycles, the guarantee of hydrogen purity, and as I mentioned before, and a side-by-side analysis for published media. And finally, this is something not already mentioned, but we talked about it previously. Given Europe's hydrogen goals, the time needed to develop new underground hydrogen storages needs quick action at the European level to enable the storage expansion. I don't know if, Manuel, do you want to add anything else?
No, perfect. Thank you very much, Rosa.
Thank you to you.
Thank you for your
Bye-bye.
welcoming play.
Hello. Good morning, everybody. First of all, thank you very much, Rosa and Emmanuel, for the discussion you have shared with us. Very interesting discussion to talk about. My name is Igor Pagazaurtundua, and I am the head of Innovation and Technology Development at Enagás. And alongside me, Mr. Guillermo Garcia-Miguel, the head of product of H2SITE, manufacturer of palladium membranes. And both of us, we will be presenting you the pure hydrogen project. The title of this project is Optimization of Purification Systems for the Storage of Renewable Hydrogen in Salt Caverns, spanning a duration of 3 years. This project has been selected by the Institute for Diversification and Energy Saving here in Spain, and with a total budget needing 3 million euros. This project will be executed within a consortium with the next companies that introduce briefly. Here we have some of them. CRS Ingenieria, a consulting firm specialized in research and exploration in the Catalan potassium basin. Iberpotas, a subsidiary of ICL Group, which operates potash and salt mines in the province of Barcelona. They are one of the major producers of potash here in Spain, with a capacity of nearly 800,000 tons per year of potash, and an extra 1 million tons of other types of salts. They own a maritime terminal in the port of Barcelona, where they export the 80% of their production worldwide. H2SITE, that is here, is a manufacturer. They develop, design, and manufacture integrated reactor units to produce high purity hydrogen. Trinity, known as Trinity Energy Storage, they are specialized in promoting, operating, maintaining energy storages, very active right now in relation to renewable gases and in particular hydrogen. And at last but not least, Enagás, the project coordinator, the Spanish TSO with more than 50 years of experience managing extensive pipelines networks, underground storage and regasification plants. Following the Royal Decree 8/2023, is the provisional hydrogen transmission network operator, on obviously promoting renewable gases projects and infrastructure, and in particular green hydrogen. I will explain briefly the scope of the project. After that, I will give the floor to Guillermo. We will have 5 minutes to ask questions each other. Okay. The scope of the project you can see on the slide. First of all, we will analyze, we will study for a favorable area in the Ebro Valley, close to the province of Barcelona, in order to identify the perfect place to develop salt caverns, in order to store green hydrogen. Once this is done, we will extract various samples from these salt layers in order to to analyze and to try to reproduce in real operational conditions what the membranes will have to handle. Okay, not only the membranes from H2SITE, but another types of membranes. Okay. Apart from that, various of these samples will be studied for other environmental and technical aspects of the project. Okay. And finally, once we have these studies done, we will test in an industrial scale the different membranes, the ones from H2SITE, the palladium ones, and as well the carbon membranes. Okay. So thank you very much. Please.
So thank you, Igor, and thank you, Enagás, for the invitation today. So yeah, the project that we have on our hands today is very important for us. It is explaining how important it is for the industry to develop this kind of infrastructure. And as Igor was saying, in H2SITE, what we do is we develop the technology, design and manufacture the integrated reactors that purify the stream of hydrogen. So it would mean that if you have a blend of hydrogen, or you have an energy carrier that contains hydrogen, at the end of our membranes, you will have pure hydrogen. So in a nutshell, we can deal with this separation or this integrated reactor operations, but it's all based in the membrane. So what you see on the left is that membrane that is a solid membrane, or in reality it's a metallic membrane that only allows hydrogen to go through. So if you see any of the typical membranes, you may have pores that will allow certain diameters to go through. But in this case, you have something that is solid. So it means that only hydrogen can go through. The moment that you have something that is solid and only hydrogen can go through, it means that at the end of the membrane, you will have only pure hydrogen. So it obviously depends on how many you put and how you make it in order to make it more efficient. The other benefit is that these membranes can be integrated with catalysts. So if you put some of the catalyst inside the reactor, it will tweak the reaction in order to make it more efficient thermically. So you will have more efficient hydrogen produced from ammonia or other things. But today is about purification, and how do we make it happen? When we put the membranes, we manufacture them and we put it in bundles in order to create more surface in the smallest possible area. And this is how we create more permeability for the membranes. Then we put it in a reactor, and this is the reactor we design to make it to the conditions that will allow it to produce more hydrogen in a more efficient way. And finally, put it in a system, and this system goes into the site. And when you connect one of the flows and the other flow, in the exit, you will have hydrogen. So this is all the magic. So it is all about making it easier and making it so that within a small unit, you can produce high amounts of hydrogen. We are not alone in here. Obviously, there's technologies that have been developing for years, and how do you separate hydrogen has been done for ages with PSAs. But those PSAs were developed for the uses that are required at the moment. So those uses doesn't require pure hydrogen. If you want something new, what we are seeing is the fuel cells and other systems like direct reaction, etc., are going to require higher purity in the end use. So if we want to get to supply these uses, we will need to rethink how do we produce. The membranes that we produce, as I was saying, produce high purity hydrogen, but it's not just that. So if you have a blend that contains less than 2% of hydrogen, you still can recover 98% of the hydrogen and produce high purity hydrogen. Also, the permeation that we can offer with these membranes, it is far bigger than what you can obtain with others. And it means that you can produce more hydrogen in a small footprint, which is one of the constraints as well that we've seen in the industry. And just one more thing. Our membranes are attracted to hydrogen, as I was saying. So, for example, things like helium that are really difficult to separate can be separated with our membrane. So you can have a stream that is only helium and only hydrogen, but you have the two. And well, this is just an explanation of how do we compare the LCOH and how do we show it compared to other technologies. So to us, it's a race in order to allow the industry to develop the options that are required for those new uses and how the other technologies are developing for those technologies. So we think that we're better suited for that, but obviously it's a case of finding the numbers and have their own case. In this particular case, for blue hydrogen, we're going to be analyzing those options, no? And we're going to put to test our membranes to different range of specifications. Starting from the pressure, so from 50 bar to 160 bar, more or less, is what we're going to find in those salt caverns. Also, the conversation prior to ours was about the possible contaminants that you may find in there. So we will need to analyze once we find out what is going to be there. And therefore, in the end, having testing, how many membranes do you need in order to produce all those, that amount of hydrogen? If you put in perspective, a flow of nearly 500 tons per day of hydrogen, it is a lot of hydrogen. So it needs to be tested and it needs to be escalated. Finally, this test is going to allow us to do that. And all the testing that we're going to do are for our membranes, for the H2SITE membranes, and also the Technalia. We come from and we were partner. Also the carbon members that they got there something to compare how the two look compared to each other. No? And there's going to be for the different ratios, compositions, and the aging.
Okay. Okay, thank you very much, Mr. Guillermo. I would like to ask you one question. No? As Emmanuel and Rosa have been talking before, there is a debate in Europe right now among hydrogen transmission network operators of what should be the minimum purity required to be carried within the high pressure pipelines. No? 98% or the 99.5%. I would like to know if the development of your palladium membranes have reached this 99.5%. As far as I have understood, we are very close to that. But there is another question related to that one: is which will be the increase in both CAPEX and OPEX, investment costs and operation and maintenance costs, if we go from 98% up to 99.5%, talking about your technology. No, I think this will be interesting. Apart from the impurities that your membranes could handle or not, this is something important to be analyzed. No?
Yeah, so it's a very interesting technology because, question, because it is what the industry wants to get to, no? And how it is going to be more efficient for everyone. As you were saying, for us, the answer is very easy. No? So the pipelines are required because there is new uses of hydrogen, and those new uses of hydrogen will require the highest purity. No? So you want to get to the highest purity as early as possible. No? So you don't need to transport something else that is not going to give you the heat that you need in your final process. So if you want to reach that purity, you want to reach the highest purity at the beginning, and you have different technologies to do that. Without technology, we always get in 99, 97 or higher. So if you want to get 99.5, if you want to get 98, well, you're going to get higher anyway. If you're using other technologies, then you will start thinking about different cycles. If you're talking about PSAs, or how is it going to handle the last phase of the purification process, as if you were talking about polymetallic membranes, or in other cases, how are you going to handle that huge volume of hydrogen that you're going to extract. So each one will have its phase, and we believe that in order to make it cheaper in the end for the end user, you need to go to for the higher purity.
But okay, thank you very much for your answer. I have another one, because obviously when we are talking about huge scales, high flows. We know that the technology is evolving, but where are you? I mean, where are you, and where are you going to be in the next coming years? Because we do not need only kilograms. We need hundreds of tons, and is what we are looking for. No, so scalability is another challenge, no, that should be handled.
Absolutely. So yeah, I think that we are in a good point at the end of our technology, because we need to scale our technology, but the industry also needs to be more higher. So there's no point of storing green hydrogen if you're not producing green hydrogen. So since that is going to take some time, we have some time to escalate our technology. So at the moment, we've been doing projects starting some years ago when we were doing kilos of hydrogen, a very small amount of kilos of hydrogen per day. We are now going to we have done units for 200 kilos, and we are developing this year units for 2 tons of hydrogen per day. But we are already developing our projects for 20 tons, 200 tons, and eventually thousands of tons. No? So in the end, at the beginning, what you want to demonstrate is the durability of your membranes. So the longer that you can test it, the better, even if it is for a small amount of hydrogen. And we have tried that for thousands of hours. And we have created thousands of units of membranes, no? Preparing our factory in Bilbao. And as we go up, we have developed the membrane, and we need to develop the case, no? And the case gets more important as you go higher in the production. As I was saying before, the next step is the reactor. So how do you standardize that reactor? And then the balance of plant. How do you make more efficient that heat integration, etc., that you're going to be handling when you go to those stages, and hopefully in a few years we'll be at the same time in the right level.
Okay. Thank you very much. I don't know if you have any other question, but from my side, happy so.
Yeah, thank you very much. Congratulations to our speakers, to Emmanuel, Rosa, Guillermo, and Igor, for your interesting exposition. Okay, this is the final of this workshop, but we hope there will be a lot of workshops in the next months. And I would like to invite you, if you are listening to us, to put in contact with Igor, or coordinator of this Hydrogen Technology Observatory, to showcase your projects of technological around the hydrogen. And thank you very much to everybody. Okay.